Okay. Hello, everyone. Thanks for coming. I'm Cheng-Han Hsieh. I'm a second fellow at UT Austin, working with the open learning. So today I will talk about the giant planet formation time window from the observational perspective. So one of the big questions in astronomy is to search for exoplanets outside our solar system. So until last week, TASS and Kepler have detected around 5,800 planets. And here's the plot for orbital period versus the planetary mass. So just from here, you can see there are three populations of exoplanets detected so far: hot Jupiter, cold Jupiter, and super Earth, sub-Neptune planets. It's important to point out that until today, there's no true solar system analogs yet. You can see that here are the solar system planets. They are occupying a different parameter space than the detected exoplanets. And if we look at the lower mass regions, in 2017, Fulton detected a radius gap around 1.7 Earth radii, separating the supermass and the sub-Neptunes. And these different types of planets, they have like different radius as well as the density. And in 2018, if we look at the TASS and Kepler planets, there seems to be some pattern in them. These systems of tightly packed inner planets appears to have correlated size, mass, as well as the orbital spacings. So until today, there are still a lot of unsolved mysteries. To understand the populations of exoplanets and their orbital properties, it's very important to look at how they form, to look at the planet formation. So planetary systems are formed inside molecular clouds, which is a collection of dust and gas. And here shows an image of the Orion molecular cloud. And inside the molecular cloud, if we continue to zoom in, and there's a lot of filamentary structures. The molecular cloud is very turbulent with supersonic turbulence with Mach number around like 8 to 10. And if we continue to zoom in into the most dense regions known as protostellar cores, and inside these protostellar cores, there are rotating disks surrounding the central protostars. So here shows an image from JWST of an edge-on disk. And inside these disks is where the planet formation takes place. So when we talk about these disks surrounding the protostars, these disks are mostly made up of gas. 99% is mostly hydrogen and helium, and 1% of heavy metals. So heavy metals in here mean dust. So inside these disks, there's some dust settling going on. There's grain growth, there's turbulent transport, as well as the radial drift. So there's many different processes inside these disks. So currently, there are two groups of models for forming planets. So one class of models form the planet top-down. So you start with a very core, protostellar core, and when its mass is greater than a gene's mass, it will start to collapse and form a disk around the central protostar. And if the disk is very massive, it will start to fragment, and some of these surviving fragments will later become giant planets. So this class of models are known as disk fragmentation, and they form the planets from top down. So the other groups of models, they form the planets from bottom up. So you start with small dust grains. These dust grains will coagulate and form into larger pebbles, and then it will continue to grow into planetesimals and then later form planets. So another groups of models, they form the planets bottom up. And these groups of models, one example is the core accretion model. So in 2023, Drakaskova et al. In Protostars and Planets 7 chapter, she gives an overview of the core accretion model. So on the x-axis, plot the size of the dust. So you start with micron-sized dust, which is the typical size in the interstellar medium. And these dusts will start to stick onto each other, coagulate, and form millimeter-sized dust. And once they reach around like a meter, the Stokes number is around 1. So a lot of them will spiral inwards towards the central protostar. So to prevent this, people come up with ideas such as the streaming stability. And so if you have pebble to dust to gas ratio around 1, and you can start to have streaming stabilities, and the localized collapse will form larger planetesimals around kilometer size. And these planetesimals will continue to accrete the pebbles, and then once it reaches the pebble isolation mass, then it will start to have a runaway growth accretion for the gas. And eventually they will form gas giants. So here shows like a theoretical plot from Raymond in 2020. And the y-axis is the time. So you can see it started with like very small micron-sized dust in the interstellar medium, and then dust coagulates, becomes larger, and then streaming stabilities form larger planetesimals of kilometer size. And then you continue to have pebble accretion, and then once it reaches the pebble isolation mass, then you will have you will start to increase gas, and then with the runaway growth, and eventually form giant planets. So one of the major problems of planet formation is that while we can have these pictures from theory and simulations, there's still lack of observational time step. It's hard to, from observation, to tell when the planet formation should start and when the planet formation should end, and at what time the dust should be, like what size. Until today, there's still a lack of observational constraint to pinpoint the whole process. So this is one of the bottleneck, and to see how like planet formation in progress, we need to look at the protoplanetary disk, which is where these protoplanets are formed. So in 2014, there's a groundbreaking HL image showing a lot of substructures. So this is the most updated version from Ian Stephen's 2023 observations with ALMA, with 25 hours of integration time. So you can see the very beautiful disk with a lot of substructures. These substructures are the ideal place for protoplanets because they correspond to pressure maximum, they have concentrated dust grains. And in addition, these substructures could also be created by protoplanets. So there are possible hints for the hidden protoplanets. So here's a simulation by Dimitris, just showing that if you put a planet inside the disk, it will start to generate like spirals and then rings and curve out substructures. So looking at these substructures, they are the ideal formation site for protoplanets, and also they could be a possible hints for the hidden protoplanets. So it's very important to point out all the past observations mostly focused on the large luminous disk or more evolved disk with ages greater than 1 million years, mostly class 2. For example, the famous D-Sharp survey led by Sean Andrews as well as the Odisha survey by Hsieh et al. In 2021. So recently, we start to have big efforts trying to search for substructures in the youngest class 01 disk. So this was a large ALMA large program led by Nagashi Ohashi, the eDisk survey. So on the right-hand side shows the 20 sources, class 0 and 1 sources, surveyed by the eDisk. And as you can see, most of the disks are pretty smooth. They don't really show much substructures. And so this is possibly suggesting that substructures in younger disks are hard to find. So it's very important to point out, until today, we do not have a uniform high angle resolution search for the disk substructures in the youngest class 0 and 1 disk. But studying them is very important because it tells us how early does these disk substructures form, and as a corollary, how early planet formation begins. Yes.
From here, it's hard to see. What are the scale bars? How big are these disks?
So this is a 20 AU.
Okay.
Yeah, the scale bar is 20 AU over here.
And sorry, just a similar question. So HL tau at this sensitivity and resolution would or would not see the substructure?
So the resolution for eDisk is around 7 AU, and HL tau is observed at higher angle resolution around 3 AU. So there's a factor of 2. But I don't think if you increase the angle resolution by a factor of 2, you're going to see substructures in these.
Based on what?
It could be optical depth and
Sure.
Yeah.
That's yet another, but like, I guess if you took the D-sharp survey and smoothed it to this resolution, many of those disks would still show substructure.
yes. Okay, so in order to talk about how early does the substructures form, it's important to talk about how we trace the evolution of protostellar systems in the youngest class 0 and 1 sources. So in the early stage, we have a lot of materials in the envelope surrounding the protostellar systems. And once it reaches the Jeans mass, it will start to collapse and then forming a disk. So in the class 0 phase, you have a disk and also like informing envelope as well as a narrow protostellar outflow. And during this stage, when you look at the spectral energy distribution, the SED, the flux you will be seeing mostly corresponds to the cold envelope. So it's emitting at the longer wavelengths. And as the protostar evolves, the density of the envelope drops, and you'll start to see emission from both the disk and the central protostar. So the disk will mostly emit in the infrared emission, spanning around 1 to a few hundreds of micron in terms of wavelengths, and the stars will emit around less than 1 micron. So in the class 1 phase, you'll start to see a lot of emission from the disk, infrared emission, as well as some emission from the star. So we use the SED, the change in SED, to trace the evolution of the protoplanetary system. So this is how it works. So in the early stages, you mostly see the thermal emission from the envelope. And as the protostellar cores decrease in density, you can start to see more infrared emission from the disk. And then later on, the emission from the central protostar. So to quantify the change in SED, so people come up with an idea called bolometric temperature. So this was proposed by Phil Mayers and Lada in 1993. So the bolometric temperature is the temperature of black body having the same mean frequency as the observed continuum spectrum. So imagine you have a change in SED, and then you imagine like fitting some kind of black body curve to get like a temperature for that SED. So this is just an idea to quantify and make it into one number. So as the protostellar system evolves, you will start to see shorter and shorter wavelengths from the infrared emission of the disk, as well as the central protostar. So the bolometric temperature will increase over time. So this is a tracer for the evolution of the protostellar system. So introducing our campus survey. So here is our campus team, me, Hector Hsieh at Yale, Australia, Hsieh, Don, Maria Jose, Mike Dalham, and Diego, PI of the project. So we use the Atacama large millimeter array, which consists of 50 12-meter dish to observe protoplanetary disk, nearly all the embedded protostars in 7 nearby molecular clouds. So Chamaeleon 1, Chamaeleon 2, Ophiuchus, Ophiuchus North, Aquila, corollary Australis, and Serpens. These are from the Spitzer C2D Legacy Survey, the catalog published by Dalham et al. 2015. So we're covering the full class 0, class 1, and flat spectrum sources, as well as the early class 2 sources with bolometric temperature less than 1,900 Kelvin. So in total, we detected 184 protostellar disk. And the survey data paper was published in my 2024 paper last year. So here is our comparison of our campus survey with the 3 other survey. So the famous D-Sharp survey and Odisha, they have very high angle resolution. The angle resolution, linear resolution is around 4 AU. And the eDisk large program, they have angle resolution around 7 AU. And our angle resolution is a bit lower. Our angle resolution is around 15 AU, but we have 90 sources. So the sources is way more compared to the D-Sharp and Odisha and eDisk. So another important thing to point out is that the 90 sources in our survey is uniform. So with this uniform sample, and we can start to conduct statistical search for protostellar disk substructures in the youngest class 01 phase. So here are some of the disks with substructures found in our campus survey. So I aligned them by age. So the youngest one are class 1s shown on the left, and then flat spectrum sources, as well as class 2 sources. So, and from the sample, we found, interestingly, the multiple ring systems tend to be larger than the other types of morphology. So this could be intrinsic, or this could be due to observational bias, because the larger disk, you can resolve multiple rings, but if the disk is too small, then you couldn't see them. So this is an interesting trend that we see from our data. In addition, if we look at all the sources, there seems to be 2 populations of substructures. So one is like a donut shape with a large central cavity, and the other type of substructures are centrally filled. And we see them from class 1 all the way to class 2. And this is ALMA band 6, so 1.3 millimeter. So all these emissions are from the thermal dust grains. So this is not due to the free emission from the jet. So this is something very interesting. We don't know what kind of planetary systems will they evolve into, and which one resembles our solar system. And another interesting findings is that we found that multiple ring systems tend to be centrally filled. So if you look at all the multiple ring systems, you don't see a large central cavity inside these multiple ring systems. And even if you go to higher angle resolution, you don't see like a huge central cavity occupying like 25% of the disk inside these multiple systems. And this is something very interesting. We don't know why, but this is possibly tied to its like formation mechanism. And this is definitely something interesting to investigate further in the future.
Yeah, if you can come back one slide. So I don't know how much do we have the star measurement of the disk? Is to say, can we distinguish between single or a binary stars? Because I don't know.
Yeah, that's a very good question. So all the sources here are single protostar, but this is down to around 15 AU because our angle resolution is 15 AU. So if there's a tight binaries, we wouldn't know.
Okay.
But there's no binaries with orbit greater than 15 AU in these systems.
I see. Okay.
Okay, so in order to study, to do like a uniform study of these substructures, it's important to take into account of the effective resolution. So in Bate et al. 2023 PB7 paper, he showed that majority of the disk without substructures have been observed at low effective angular resolution, less than 3. So meaning that if you sample your whole disk with only 3 measurements across the disk diameter, you're not going to see much substructures. So this is something to take into account when you do the search for substructures. So we limit the effective resolution to be around 4. So meaning that for every disk, there are at least 4 measurements, 4 beams across the diameter. So in addition, it's very hard to detect substructures for edge-on disk. It might be possible, but it's very difficult. So that's why we exclude the edge-on disk with inclination angle greater than 75 degrees. So here is the main result from our campus survey. This is our campus survey plus the literature data from eDisk, DShop, and Odisha. So on the y-axis, plus the disk radius and disk mass. The x-axis is the bolometric temperature, which you can see as like a time axis. And then I draw the line for class 0 and class 1, and a dotted line to divide different class. So the division between class 1 and class 2, that's based on alpha. So here I plot around 650, which is proposed by Chen 1995 to be a division between class 1 and 2. And so the blue symbol represents the disk with substructure. And the orange is the one without substructures. And the black cross represents sources that are compact, which have diameter less than 4 beams. So just from this plot, you can see substructures start to appear around bolometric temperature of 110 Kelvin. And that is very interesting because this corresponds to an age around like 0.1 to 0.2 million years. So this is telling us that substructures appears way earlier. So if you look at the current literature, people think that the substructures appears between class 1 and 2, but that's not the case. Substructures appears in the early class 1. And we start to see this because our linear resolution is around 15 AU. So if we look at the past survey at 40 AU, then you don't see much trend. So this is at 40 AU resolution. I combine our campus, Serpens, and Aquila sources with Orion A and B. And then you can see like nearly all of them don't have substructures. There are a few of them that shows a ring with a central cavity, and those are very large rings. So this is reported by Cheng-Han et al. In 2020, found in the Van Den survey. And they found that these large rings and cavities has a size greater than 50 AU. So instead of being induced by planets, it's more likely these large-scale substructures is created by close separation binary formation at early times. So we look at when do the substructures first appear? Another important question is to look at when do most protostellar disks have substructures. So the transition occurs at around bolometric temperature of 200 Kelvin. That's when most of the disk starts to have substructures. And this corresponds a time around 0.2 to 0.3 million years. So it's in the early class 1 phase. So it's important to also look at both the effective resolution as well as the linear resolution. So here I plot the effective resolution of the sources as well as here the flux of the source, which is proportional to the mass. And color-coded by linear resolution. So first of all, if you look at the class 0 sources around here, that regardless of the linear resolution, you don't see any substructures. And if we only focus on the green point, then you can see after around 300 Kelvin, all the green points except one have substructures. So this is telling us that by T-ball around close to 300 Kelvin, which is around 0.2 to 0.3 million years, a high fraction of protostellar disks have like 2 to 3 AU size substructures. And the next thing I did is I classified the substructures into different morphologies, a different class based on morphology. So there's spirals, multiple rings, ring with a central cavity, and embedded ring in disk. So I plotted them as a function of bolometric temperature, and you can see that they're all scattered across the whole plot. So the only tentative trend that I found is that you can see the rings with disk with multiple rings tend to be larger than the ring with the central cavity. But this is a very small statistics, and also this could be due to observational bias. So Hsieh et al. In 2019, they proposed an evolutionary picture. So you start with like a smooth disk, and then over time you start to develop a lot of shallow substructures. You start to see a lot of like rings, and then the dust starts to accumulate it into one of the rings, and then you start to see these type of like embedded rings. And over time, due to radial drift, you're left with like a ring with a large central cavity. So if this is the case, then we expect to see multiple rings towards the left, followed by the embedded ring in disk, and the ring with a large central cavity, they should show up on the right. But that's not what we're seeing. Instead, we see a lot of substructures are mixed together. So instead of a single evolutionary picture, the data tends to suggest that there are multiple populations of substructures, possibly generated from different mechanisms. And it's important to point out, our sample is only complete for mass greater than 0.01 solar mass, for disk mass greater than 0.01 solar mass, which is above the minimum mass solar nebula. Minimum mass solar nebula is the minimum mass to form our solar system. So for the low mass disk, we don't really know do they have substructures or not, because they are very compact. And this is something that's I'm interested to study it further in the future, because these low mass disks, it's more likely they're forming icy sub-Neptune or rocky planets instead of giant planets. So it'll be interesting to see how the planet formation in low mass disk differs from the one forming giant planets. And is there a lag between the substructures when substructures first appear, or what kind of substructure do you see in the low mass disk? So these are interesting questions that haven't been answered yet. And another important thing to consider is that the transition of these substructures at early class 1, it could be an upper limit. So it could be early on, the disk is optically thick, and this hides the substructures. So in order to test this, we compute the brightness temperature using the full Planck equation. And then we obtain the dust temperature from Tobin et al. 2020 to get the dust temperature, and we divide the ratio to get the rough estimate of the optical depth. And we see that there's no transition at around 200 Kelvin. So we suggest that this transition with and without substructure is not due to the optical depth effect alone. But it's important to point out that this method is very simplistic, and we need multi-band ALMA observations to calculate the spectral index and to actually know whether the disk is optically thick or not. So just to keep in mind that we see substructures start to appearing in early class 1, but this could be the upper limit. Substructures could appear early on if the disk is optically thick.
Okay, so I mean, this is nice. I mean, a nice demonstration that that's not the entire story, at least from the perspective of the optical depth in the disk. But what about the presence of the envelope? Is the bolometric temperature at which you observe this transition consistent with the possibility that substructure could be hidden by the envelope? Or do you think that would be captured by this measurement?
Well, we're not that worried about the envelope, because for interferometer, we can pick up the smaller scales, and the envelope usually it's resolved out. And so the biggest problem is the optical depth, and also
Yeah, I guess I'm saying optical depth due to the presence of a thick envelope. So if you have a thick envelope that you're looking through, could that cause you to be both hold bolometric temperature at class 1 and also obscure substructure, so you get that correlation?
So usually when we do like interferometer, the large scale emission from the envelope will be like resolved out. We're selecting the Fourier scales that pick up only the disk size. There's some envelope contamination. There'll be some envelope contamination, but they're not that severe to blank out all the rings and gaps. It will affect the total flux.
You're worried about absorption, right? Not
Yeah.
emission.
Yeah.
So presumably the envelope is optically thick, that it absorbs everything from the disk, then your interferometer can't help with that, right?
Yeah, so these are like dust emission. So well, I don't think it's the main problem. At least the density of dust is much higher inside the disk compared to the envelope. So there are some absorption effect, but it's not strong enough to block the disk substructures.
Maybe at 1.3 millimeter, you really need a very, very high confidence to
It's called, yeah.
Another thing we did is we look at the protostellar disk substructure detection rate as a function of both the evolutionary stage and the linear resolution. So on the left-hand side, I plotted this substructure detection rate for two different linear resolution between 0 to 10 AU and 10 to 20 AU. And I only select the sources that are after the onset of this substructure at around bolometric temperature of 110 for the class 1. And just from our sample, we see that if we look at the angular resolution less than 10 AU, then we see the class 1 and class 2 have comparable this substructure detection rate. So this is telling us that substructures are formed rapidly early on in early class 1. So we talk about looking at these substructures and use it as a way to find when, possibly when plant formation starts, and what are other observational constraints that tell us about plant formation. So another interesting problem known as the Hsieh storage problem of meteorites. So this is a well-known problem in the solar system community. The idea is this: you have calcium, aluminum, and titanium. They need to form in high temperature with 1,400 Kelvin near the sun. So they have size around 0.1 to 1 centimeter. So all of them should just spirals in towards the sun within a short period of time. But we still find them in meteorites. But not only we still find them in meteorites, we found that in the carbonous chondrites, which are located far away from the sun. So this is a well-known problem in the solar system community. And in 2018, Stephen Dash in State University of Arizona, he proposed a solution. So he proposed that if you have Jupiter's 30 Earth mass core formed at around 3 AU and about 0.6 million years and open a gap, then inside the gap, the CAI will just spirals in towards the sun. And the CAI outside the Jupiter's orbit will be trapped and then eventually be incorporated into carbonous chondrites. So this is a very interesting picture. And our ALMA observations showing that substructures formed very early on supports the idea of early formation of substructure, supports this picture. So we have talked about the CAIs and what are other observational time constraints for giant planet formation. So another interesting observations comes from our sun. So this is known as the solar modeling problem. So our sun has a very metal-rich core and a metal-poor surface. So the data is very good and very precise. So the current solar evolutionary models cannot produce spectroscopic, helioseismic, and neutrino constraints consistently. So because the solar data is very good. And so Kumitomo et al. In 2022 come up with a solution. So the idea is this: early on, you have high metallicity accretion for our protosun. So a lot of dust grains just got accreted onto our protosun, and this helps build a high metallicity core. And over time, when you start to have planet formation and a lot of substructures form, these planet formations will block the dust from accreting into the protosun. So at this time, the amount of dust accreted onto the sun compared to the gas changes. The gas to dust ratio changes. You have a low metallicity accretion, and this will start to build up the low metallicity core. So they did some modeling with MESA, with our solar data, and they found that the accretion was a variable composition due to planet formation process leading to metal poor accretion of the last 4% of a young sun's total mass. So this translates to a time scale around 2.2 million years. So from their modeling of our solar data, they show that the last 4% of our young sun is mostly accreted with a little bit of dust, but mostly gas. So this corresponds to the time when the planet formation should end. So I talked about 3 different observations. One is from our ALMA substructures, which tell us about when the planet formation can begin. And I talk about the CAIs in our solar system, as well as the solar metallicity gradient. So we can start to put these together into an observational picture of the giant planet formation time window. So this is a collection of like different observations, and also some of them is my speculations. So the picture comes as this. So in early class 0, you have a very massive disk with high accretion, and the disk accretion is dominated by spiral arms. So the whole disk is very turbulent, this is a whole disk process. The disk is very turbulent, and because this is turbulent, the dust cannot settle to the mid-plane, and you don't see any substructures. And over time, when the disk mass decrease and the disk accretion process possibly change into a disk wind, which is the surface process, and then this allows the turbulence to decay, and then you have dust to settle in the mid-plane. And this is a necessary condition to start to see substructures. And also you need some mechanism to generate these substructures. And by early class 1, you start to see substructures, which is wrong. And with these substructures, the CAI can be trapped outside the rings and gaps. And this is also the time when the amount of dust accreted onto the central protostar decreases. So this is the time when you start to build the low metallicity surface for the central protostar. And around class 2 was around 2.2 million years. The neutrino flux shows that the metal poor accretion of the last 4% of the young sun's total mass. So this is the time when planet formation should stop the dust accretion onto the central protostar. So from these different observations, we can start to put together an idea of a time window for giant planet formation. So here is my conclusion. First of all, from our ALMA observations, we found that these substructures form rapidly between class 0 and 1, not class 1 and 2. It's way early. And this is only upper limit because early on, this could be optically thick. And also, there might be smaller substructures that are hidden from us. And we found multiple rings tend to be larger than this with a central cavity, but this could be an observational bias. And interestingly, our data tend to suggest there are 2 populations of these substructures. One is like a donut shape with a large central cavity, and the other one is centrally filled. And since this is ALMA band 6, 1.3 millimeter, so these are thermal dust emission, not due to free from the central jet. And interestingly, we found that multiple ring systems tend to be centrally filled. You don't see a large central cavity inside the multiple ring disk. So we don't know why, but that is something interesting to investigate in the future. So that's the end of my talk, and I'll take questions. Thank you.
So I'm curious about the lifetime of the Hayashi track compared to the accretion timescale, because I think for low mass stars, they should all be fully convective.
Yeah.
When you're contracting on the Hayashi track.
Yeah,
So how do you get low metallicity stuff stuck on the atmosphere?
Yeah, that's a very good point. So early on, the whole protostar is fully compacted. So all the signatures are washed out. But over time, the radiative zone starts to develop. And that's the time when you start to have the metallicity gradient.
But I guess I'm saying is in Hayashi lifetime is, you know, more than a mega year for low mass stars, right?
Well, and
We're talking about it like 500,000 years, right?
Yeah.
So I guess if you just plot these, like plot the isochrones, you could see where the protostars fall and then determine if that trend, like you could look for the individual cases.
yeah, and also I talked to the professor at Yale, Professor Earl, and he's been working on like solar modeling. Even in the early phases, you could have like a radiative pockets inside the protostar. But I don't know how that will affect the development of the metallicity gradient.
In terms of the observations, do you know where the RCB is in those cartoons relative to the radiative convective boundary compared to the gradient?
That is given in the paper, but
Okay,
yeah, they show the plot in their paper of the convective zone size and how that changes over time. So it sounds good.
So,
could you bring the slide to the conclusion slide? So I have a question related to the for these very old targets with large bolometric temperature, there seem to still have some disk with relatively large disk mass, but without substructures. What could be the reason for them? Or did you? My question is more like, did you exclude the disk with high inclination angles? Because if they are like edge on disk, it's never be able to detect the substructures.
Yeah, so I exclude all the edge on disk with inclination angle greater than 75 degrees. And as for why there are sources without substructures, okay, so first of all, it's important to point out that our class 2 sample is not complete. We're complete for class 0, 1, and flat. But once you go to class 2, our sample is not complete. So that's why you don't see a lot of samples over here. And second, it could be, I think that's mostly due to the resolution. So you can see these ones without the substructures have been observed at lower angle resolution. Linear resolution between like 12 to 18 for these two, and 6 to 12 for that one. And most of these are observed with angle resolution around 4.8, linear resolution around 4.8. So it could be due to the angular linear resolution effect.
Okay.
yeah, thanks a lot. That's very, very interesting. One question regarding whether you could get any handle also on the gas rather than the dust. What you're seeing is structure in the dust, and that's not necessarily related to structure in the gas in a one-to-one way. So are there any handles on?
Yeah, that's a good question. So we only have dust measurements. We don't have gas measurements for this disk because gas observations take a lot more ALMA time.
Yeah, so could these be observed in CO?
These could be observed in C18O, but you need the angle resolution like down to like 0.1, 0.2 arcsecond, which will take a lot of time. So eDisk, they only observe 20 sources, but they also have lines.
Mm-hmm.
But that makes them already a large program. So that will be, it's doable, but very difficult to do. And I don't think it's possible to do all the sources just to survey lines. You probably have to only choose a few, and that will already take quite a lot of ALMA time.
Mm-hmm.
Yeah, so far we don't have gas information. We have like lower angle resolution gas, around 1 arcsecond for all the sources, but that is only enough to trace outflows. You cannot really see much around the disk.
Yeah. So the other question that I have is of wild speculation. Looking at planet populations, it looks plausible that both of the mechanisms may be at work in some systems, or one mechanism, maybe disk fragmentation forming some types of planets and core accretion in some other systems, like perhaps the solar system formed by core accretion, and there are other systems that are really hard to make by these mechanisms, could be disk fragmentation. Could that be related to the fact that you see two different types of structures in your disks? That the final outcome of one type of your structure, the multis, for instance, would then lead to planets forming by core accretion, and the rings to fragmentation?
Yeah, that's a really good question. So I've been thinking about that as well. And one of the things that I noticed is that if you look at the positions of these substructures, these rings and gaps from ALMA, they're located at tens of AU, 30 or 40 AUs away from the central protostar. But if you look at the distribution of giant planets, they're from the California Legacy survey, they're located around 3 AU. And also one orbit across the disk at 30 or 40 AU would take too long to form giant planets. So if you want to form giant planets out, then you need like disk fragmentation. And also this could be, there's a lot of like uncertainties going on.
The timescale argument is very outdated, like as to the limit of giant planet formation for core accretion models. It's just not consistent with the pebble accretion models. And so I think saying that is misinterpreting the theory on core accretion at this point. That 30 AU is too wide for core accretion.
Oh,
And I think the selection of that, we just don't have a lot of data, right, beyond 30 AU. I mean, that's what that Fulton plot shows, right? Like the
yeah, there's also.
I think that's a dangerous argument to make, given the lack of detections out there.
Yeah, that is also important to point out. There's also lack of detections in here. We couldn't detect much wide orbit giant planets. So if you look at the first plot, the population, it's not yet complete for all the exoplanets. This one, you can see like we can only detect the most massive ones or like small ones, but close within like a 10 day to 100 day. So we still don't know what's going on in here. Yeah, so it could, there is observational bias.
We have an online question. Joan Edita at Noir Lab across the street says, beautiful results for the Quintomo et al. Results. What kind of metals depletion are they referring to? Volatiles or refractories, or can they distinguish?
Oh, they didn't do that, like distinguish. It's mostly, if it's not hydrogen and helium, and anything else is metals. In this case, they treat it as like dust.
Are there any other questions online?
Here's a question.
Just give me the online people a chance.
Sure.
Okay, Joan says thank you. All right.
Yeah, thank you. Sorry, I'm not expert about this. I work with larger scales, but I was wondering if there is a correlation between the disk size and the parent structure with they form. So is there a way that you can predict this? The size distribution can be predicted based on the property of the environment when they form?
Yeah, that's a good question. Another important thing to look at will be what the correlation with protostar mass. That would be a very important parameter. Look at what's the mass of the protostars versus like when it start to show substructures. But that is something we don't know at the moment. And as for environment, I think that hasn't been studied much yet. I look at how the outflow strands or the core mass. Yeah, so that's something that hasn't been explored much.
Okay, it's good to know because I'm interested in the angular momentum transfer.
Oh.
So I think that at some point there's like some kind of mechanism that is not efficient at some scale, and then you then start conserve angular momentum and then these form, and this should be related to some specific scale, but I'm not sure.
Yeah.
Whether
The angular momentum problem of star formation, that is a very interesting problem. That's also another project that I'm working with that often right now. Maybe we can chat.
Can we talk about this later?
Yeah, we can chat afterwards.
Dominica?
Slightly following up, but also like moving into the future. Do you have more observation, information about the central objects, and do you have spectroscopy of those stars? And also, do you plan to blow up your disks with more ALMA bands to be able to see and then explain distribution?
Yeah. So we have the SED for all of the ALMA sources, for all of these sources. So that's how we got the T-bow and L-bow. And we are planning to observe the everything in band 3 in longer wavelengths to measure the spectral index and to get the optical depth to see whether the transition is due to this being optically thick early on, or is it a real transition? So we have some projects, yeah, to follow up.
Do you have a spectroscopy of young stars?
Spectroscope with young stars, that's very difficult because these protostars are pretty embedded and they have like a very high extension. So it's hard to get spectroscopic.
Okay, it is o'clock, so anyone who needs to go, feel free to go. It's up to you whether you want to keep taking questions.
I can keep taking
Okay,
questions.
yeah. Okay.
I have one more question about binarity. Unless you consciously avoid binaries in some way, you will have a fairly high binary fraction, at least something like 30–40%, perhaps more. So how would that affect the structures, and how would that perhaps affect the interpretation also of different morphologies if you have binaries mixed in with a range of orbital parameters?
So first of all, like if it's white binaries,
Yeah.
then I don't think it will have much effect on the substructures. And if it's a binary inside the disk, then it sure should have. First of all, if you have binaries, then one hypothesis that I'm thinking about is that is that the one that was the central cavity ones could be tight binaries. So that's the one hypothesis I'm thinking about. Maybe like a lot of these ones, especially the early ones with a large central cavity, those could be due to a very tight binaries with orbits less than 15 AU.
Yeah.
So, but we don't know. We just know like within our angular resolution, there's no binaries inside the disk.
Yeah. In the class 2s, you might be able to find out spectroscopically.
Yeah. Oh, for class 2, these are there's no binaries.
These are not binaries.
These are not binaries.
So it should be interesting to also see the gas on the disk which have a cavity inside, because as you show, you can form a chain of multiple planets. And if you form this chain of super Earth or super Neptunes, for example, they're gonna carve a gap on the dust, but maybe in the gas it's gonna be shallower enough to don't see a cavity on the gas. So if you see these observations on gas and you compare and you see a cavity on the dust, but not a cavity on the gas, could be the presence of a lot of less massive planets. I think so.
Yeah. Yeah, so that would be something to like follow up in the future, to select some of the targets and do gas observations to compare the morphology between gas and dust.
Any,
Ask the
Yeah,
one last
yeah.
question. Just out of curiosity to you and also the experts in the audience, is there any model that you form a disk with substructures already, but then you put some additional parcels of gas onto the disk, additional accretion of gas? Will that change the structures of the disk or not much? Is there any model about that?
So
Because I mean, I start to see people talking about these streamers falling onto the disk. Once you've formed already some substructures, then you have a streamer of gas or something falling onto the disk. Will that change the appearance of the disk or not? Or just wonder any models.
yeah, I think Kutanova et al. Have written a paper on streamers induced substructures. And so yeah, so it's possible if you have like a lot of full streamers impacting the disk, perturb the disk, and create like substructures. But how that interact with existing substructures is something I don't know. And the whole process is still very complex. So you can have different instabilities, and you can also have like substructures generated by planets. It could be like the early substructures are generated by instabilities or streamers, and later on you can have like second generation substructures formed by like a perturbing planet. So there's still a lot of degeneracy.
If there are no more questions, thank you all for coming. If you have additional questions you think of later, Cheng-Han will be here all week, room 333, and the link to schedule meetings with him is in the announcement email for this talk. So thank you all for coming and see you all next.
Okay. All right.